Hello everyone, my name is S Maheshwara and I'm an educator at an academy. And you can follow me by downloading the An Academy learning app where you can find rest of my courses. And today we'll be discussing about the equation of the compressible flow. Also, you can rate, review and you can share this video. And you can also follow us on our YouTube channel where you can find lots of amazing videos and you can increase your knowledge base. So I'm looking forward to have a good discussion. So have a good day guys. So hello guys and welcome back, and today we'll be discussing the lesson 3 of the topic of the compressible flow. And in this one we'll be understanding some of the basic equations of the compressible flow. And once again, my name is S Maheshwara and I'm being mechanical, and this is my short summary. So to begin with, we will understand the basic equations of the compressible flow. So there are basically 4 equations, and they are the continuity equation, the Bernoullis equation, the momentum equation and the equation of state. So in this lesson, we'll be focusing on these two, and in the coming lessons, we will focus on these two topics. So now we'll focus on these two, which is the continuity and the Bernoullis equation. So in this, what we'll do is that in the end, we'll be finding the continuity equation in the differential form, and for the Bernoullis equation, one second guys, yeah. So in this also, we will find the equation from which we can equate this to the different part of the equation, which is equal to constant. So first what we'll do is that we will understand what is the continuity equation. So the continuity equation, it is based on the principle of the conservation of mass, meaning the mass, it can neither be created nor destroyed. So rho av is equal to constant. So in this, to find its differential form, we will differentiate this whole equation. So we'll get the d of rho av, and this will become equal to 0. So in this, we will divide these 3 into 2 parts. One is the rho will be one part, and this a into v will be one part. So its differentiation will be equal to uv dash plus the u dash of v. So we have written it in this particular format. So in this also, we will differentiate this av. So this will become a into the dv plus v into dA whole into rho plus av into dp will be equal to 0. So in this, if we remove the brackets, we get this as the complete equation. So if we divide this whole equation by rho av, we'll be getting this as the equation relationship, and this equation is called as the continuity equation in the differential form. And now we will understand what is the Bernoullis equation for a compressible flow. So from the Euler's equation, we have found this particular relationship. So if we integrate this, then we get the integration of the dou p divided by rho plus the integration of v into dv plus the integration of g into dz, and that will be equal to constant because the 0 will become constant upon integration. Also here, p is the pressure, rho is the density, b is the velocity, g is the value of 9.81 and dz is the height. So we get this from the Euler's equation, and in this, if we do the integration, we get this as the equation. So in this v into dv, after the integration, it will become equal to dv square divided by 2, and then this dz will become equal to z. And in this, we will keep this integration part as it is, and that is because as the density will vary in case of the compressible flow, we cannot take the value of the pressure outside, because as the density will keep on varying, the pressure will also keep on varying. So we cannot take the value of p as constant outside. So we'll be given, so we have this as the equation of the Bernoullis. Again, the Bernoullis equation is divided into 2 parts, and those are for the isothermal process, and second one is for the adiabatic process. So in the isothermal process, the temperature will remain constant throughout. Also in this, the p divided by rho will be equal to constant, which is c. So in this, if we bring the value of c down and the rho over here, we'll be having this as the equation. And this value is c1. So in this, basically what we'll do is that in the Bernoullis this equation, which is this, we will find the value of the dou p divided by rho. So in this, we know the value of rho. So the dou p divided by rho will be equal to the value of dp divided by p into c1, which we have got the value of the delta. So over here, the value of the c1 will come in the top. So we'll be having this particular value. So in this, we can take the value of C1 as outside. So the value of the dP divided by rho will be equal to this. So after we integrate the dou P divided by P, this we can replace this by log e to the log to the base e into P. So we get this as the value of the dou P divided by rho. So in this, the value of the C, we can replace it over here as the P by delta. So we get this as the value of the P divided by rho into log e to the power of P. So basically what we have done is that we have found the value of this particular part. So to do that, in this we have taken the value of the P divided by rho to be equal to constant. So in this we got the value of this tau over here and the C over here, and we got this as the value of the tau. And after we found the value of tau, we replace it over here. So we get this. So in this, the value of C1 will come on the top. So after we simplify this particular part, we get this as the value of the dou P divided by rho. Over here, the value of C1 is equal to this. So we will replace this. So we get this to be equal to this. So we will replace this value over here in the Euler's equation. And after we do the integration, we get this as the Bernoullis equation for the isothermal process. So in this again, if we divide this whole thing by G, then we get this as the final equation. So this is a very important equation, guys, and we will be using this to solve the isothermal problems. So in this, if we consider this equation for 2 points, so in this we will replace this by 1 by rho 1, P1, V1 and Z1, and this will be equal to P2, V2 and Z2. So for the 2 points we will be having this as the equation. So for an isothermal process, this is a very important this equation, so you have to remember this, guys. Now the second one is the Bernoullis equation for the adiabatic process. So for an adiabatic process, as we all know, P and that divided by the rho to the power of K will be equal to constant, which is C1. So in this again, we will get the value of C over here and we will bring the value of rho over here. So we will be getting this as the relationship. And in this, we will do to the whole power of the 1 divided by K. So this rho will become equal to 1 and this will become equal to the power of 1 divided by K. And we will replace this value of rho in this. Again in this so in this also we want to find this particular value. So first we will find the value of this particular rho. So from this part we got the value of C1 over here, and then we found the value of rho to be equal to this, and then we replace this rho value over here. So we get this as the equation. So in this, the value of C1 will come on the top. So we'll be having this as the value of the dou P divided by rho x. So over here, this value will be equal to the constant. So we will take it outside. So in the base, we'll be left with P to the power of 1 divided by K. So if we bring this on the top, we'll be having this. So after we integrate this part, we get this, which is P to the power of T minus 1 divided by K plus 1, and this whole divided by T minus of the 1 divided by the minus of 1 divided by K plus 1, because the integration of the a to the power of n will be equal to a to the power of n plus 1, and this whole divided by n plus 1. So we have done this in the same case. So after we simplify this, we get the value to be equal to this. So this will come over here, and this will we'll have the value of the k minus 1 divided by k, and the same thing also we will get it on the base. So k and minus of 1 and this whole divided by k. So we get this as the value of the dou P divided by dou x. Now what we'll do is that we will bring the value of this k on the top. So we'll be getting this as the equation. Also in this, we will replace the value of the C1. So if we see in the beginning, we get this as the value of the C1. So we will replace it over here. So we will getting this as the equation. So what we are trying to achieve is, we are trying to write the complete part in the form of K and in the form of the P and rho itself. So to do that, we must first remove the value of C. So we are writing the value of C in terms of the pressure and the density. So after we replace this, we will simplify this part. So after we simplify this, we get this as the value. So over here, this one and this one will get cancelled, and this k will get cancelled. So we'll be having dp to the power of 1 divided by rho. So we get this as the value of the dp divided by rho. And since we have found the value of the dp divided by rho, we will replace this in the Bernoullis equation. So for the compressible flow, we get this as the complete equation. So in this again, we will divide this whole equation by g. So this is the simplified version. And guys, this is a very important equation, and we'll be using this to solve all the problems which will be based upon the adiabatic process. So if we have two particular points, then we will replace the value of this p by p1 and this v by v1 and this z by z1, and we will equate that to the second point, which is the p2, v2 and z2. So this is a very important equation. So guys, I suggest you that you go through this whole part slowly by pausing the video so that you can get a proper understanding. So in this lesson, there are two things which are very important, and those are the Bernoullis equation for the isothermal process, which is this, and second is the Bernoullis equation for the adiabatic process, which is this. So these two are very important equations. So guys, if you had any sort of doubt in this lesson, then you can feel free to ask me, and you can rate, review, and you can recommend this reference, and you can also follow me. So in the end, I'd like to wish you luck, and I wish you to have a very productive day. Thank you.